To try to keep track of it. So we're just going to draw classical pictures, but now I want to say something that Feynman taught us, that you should think of these particles as they move along in space and time, sometimes breaking into two, and sometimes rejoining. So here one particle broke into two at this moment, and two rejoined into one here. The overall process is that two came in from the past and two went out to the future. So that was a scattering process. And Feynman taught us how to calculate quantum mechanical probability amplitudes for every such picture. Well, the thing about them is that everyone will agree that there were definite space-time events where something happened. One particle broke into two, or two particles joined into one. And those events are what you might call technically singularities in this graph. They're distinguished events. And standard quantum field theory needs special rules for what happens at those singularities, which is the basic limitation of its predictive power. Even after I tell you what the particles are, you don't know how they interact. Because to know how they interact, you would need to know how they're allowed to break and join. And that's a separate question. In string theory, the setup is a little bit different. Each of these particles is replaced by a little tube, which describes the history of a propagating string. And where a particle breaks into two discontinuously, a string can smoothly split apart into two strings. And then here's another one coming in. And then they go out. So now I've drawn a space-time picture of two strings coming in the past and two going out in the future. And the point of this picture is meant to be that it's all perfectly smooth. Unlike this one, which has two discrete events at which breaking or joining happened. So the result of that is that if you know what the string is, you also know how it interacts. You know what it's allowed to do. But if you know what the particles are, you still need a separate recipe for how it's allowed to behave. So that sort of is the germ of the fact that string theory is much more predictive than standard quantum field theory. You don't need to separately say what the objects are and how they behave. Once you've said what the objects are, how they behave is completely defined.